Yeah. So we will start today. So till now, whatever is this, whatever is done in this course, that is the system of linear equation, row reduction process, row equivalence, row spaces, and row reduced echelon form, and as well as the vector spaces and the dimensions and linearly independent, linear independent dimensions, all these things. Now, in that is up to the week 2 content. Now, week 3 content is on the based on the mainly linear transformations and algebra of linear transformations and little bit of matrix representation. But I don't think that much is done in matrix representation. There is lots of thing in matrix representation. So today we will discuss some of the problems which is related to the week 3 content, so that those things will help to you solve problems in the week 3 assignment of the week 3. Okay, so till now if you have any questions you can ask also. Okay, if you have any specific questions of that assignment, I will not be able to give you the proper exact solution, but I will try to solve the similar problem which will help. Okay, so
Sir, I have a one question.
yeah, please.
In problem number 7, assignment 3,
uh,
V is a vector space of polynomial at
hmm,
most degree 3
hmm,
and B is the basis 1
yeah,
plus x square plus x cube,
hmm,
x plus x square, x cube and 1.
hmm,
But these four elements are linearly dependent, sir.
yeah, that's true, that's true. So is it a order basis of V? How this is order basis then? um, X plus x square, yeah, that's true. Just 1 minute. Let me just read the problem. Let V be the spaceable polynomial functions of degree less than equals to 3 over the field F. So that will be the four-dimensional vector space, and W be the space of all four tuples over the field F. F is not mentioned, but it is supposed to be either real or complex. And B1 equals to 1 plus x square plus x cube, comma x plus x square, comma x cube plus 1. So the first vector is equals to sum of the last three vectors. So they are linearly dependent then. 1 plus x square plus x cube. That's true. And B2 equals to, yeah. So last date is 12, right? So I'll talk to the
Yes.
faculty today, okay, after the class.
Okay.
And if there is any problem, either a announcement will be uh, given from, will be given from that side, from the faculty side, or um, I will give a, I'll mail in discussion forum. Okay, don't worry. I think this is, you
Okay.
are saying B order basis of V and W respectively. So first one is not order basis, but the main question is that let T be a linear transformation defined by T one x equals to this, x square equals to this, x cube equals to this. Which of the following makes an isomorphism? How can do this type of mistake? This is mistake, really mistake. Yeah, thanks. I'll talk to faculty, and if even if the question is by any chance, I may found the question is correct. So what is your? I can also in that situation also I will mail. Okay, don't worry. Okay,
Okay.
or main discussion forum. Maybe not today, but after tomorrow I will mail obviously. But 12 is there. Okay.
Okay.
So any other questions? Okay, so then I'll discuss similar questions. So in week 3 content there is starting, just a minute. Week 3 content is starting with the linear transformation. So let's start with the definition of linear transformation. Just a minute. What happened? Okay, just a minute. Okay, just I will just join from, there is problem from this side. Okay, okay. Okay, so thing is started with the linear transformation. Linear transformation. What is the definition? I will not discuss anything related to, I mean, anything not that much in that in definition portion, but I will try to do quickly to the problem. Okay, let V and uh, let V and W are two vector space over a field F. Okay, a linear transformation from V into W is a map or function. Okay, that should be a function, but with some certain condition. Function T from V to W such that T of C alpha plus beta is equals to C of T alpha plus T beta. Okay, T alpha means T is a function I am talking about. So T is here is means T of alpha plus T of beta. This should satisfy for all alpha comma beta in the vector space V and all scalar from the field F. Okay. Example, one can give any example, just like let's consider an example. Um, Example that let's take V is equals to the vector space R to the power 4. That means tuple of 4 element and over the field R, and W is equals to, one can consider that is also the tuple of 4 over the field R, or one can write this is as tuple of 5 over R. That can be also, but one can one can consider anything. So now consider T V from W. How one can give? Let's consider map T any element in x R to the power 4 or V, that will be like this way: x1 x2 x3 x4, that will be equals to um, x1 x2 x3, that I'm just writing, for example, x1 comma 0 comma 0 comma 0 x5, this way. Then check that this will satisfy the condition above here. This condition will be satisfied. Check, this is vector space. Okay, this is a linear transformation. This is a linear transformation. Okay. So one problem will now, on the basis of this, I will discuss one problem which give whether a map is linear transformation or not. This is a map. Okay. So okay. So this is suppose the problem number one, for example. So now what will be the whether which of the following functions T from R to R are linear transformation? This is the questions. So so first question is, let's T is a map from R to R. Here is also R square is the vector space that is of tuple 2 and over the field R. So now T, for example, the first condition, let's take A, that is given by T A comma B. Yes,
Only third.
only third, yeah, that will be because here is the b cube, so that's why that will be restricted. Here is 1 plus, that will be the restriction, and here will be minus 5. So, but we'll just discuss a little, I mean, case by case. So, consider two element a1, b1, and another element a2, b2, that is inside the element r square. Okay. So, so let's consider another scalar element that is coming from the field F, that is actually R. So in that case, C A1 plus B1 plus A2 comma B2, this element, what this will be, this supposed to be C, to form a vector space. We should have this one, right? We should have this one. To form a vector space, we should satisfy the above equation. To form a vector space, T should satisfy the above equation. Satisfy the above equation. Okay. But what is happening? So in the on the left hand side, what will have C A1 plus A2 comma B C B1 plus B2, right? This is the thing, C B1 plus B2. If in the case of A, this is equals to A, that is the first one, comma A2, and the other element is C B1 plus B2 minus 5. This is the thing, and C T A1 comma B1 is equals plus T A2 comma B2, that will be C times A1 comma B1 minus 5, because T A1 comma B1 is A1 comma B1 minus 5, plus, and the second one, that says that T A2 comma B2, that will be A2 comma B2 minus 5, minus 5. This is the thing. So it will be CA1 plus A2. That's true. But the second one will be CBO1 minus 5C plus B2 minus 5. So this second term is not equal. Okay? This is not equals. So therefore, here one can take A1 B1 belongs A1 B1 is an element, and A2 B2 another element from the vector space R2, such that T C A1 comma B1 plus and C, if we consider C is 0, then there is nothing, but C we can choose C that is not 0. Okay, we can choose suitable C such that this is not equals to C times T A1 comma B1 plus T A2 comma B2. So that's why first one will not be the option. Similarly, one can show the second one will also be not the option, and third one also not. Why third one will not be, that should be clear, because here is the minus 5 thing, here is plus 1. So similarly, this will create problem on the right hand side, and the third one is not the option because B cube here. So I'll check the second option also, but similarly I'll just write similarly. mm
So T of alpha x is not equal to alpha of Tx, alpha times Tx.
Here one condition can be easily given, right? That's true. One condition can be given.
Yes, sir.
Similarly, so
For
but
fourth one, and yes, sir.
yeah, fourth one is also, I think
Yes,
fourth case C alpha. Fourth case is
yes,
also
sir. That one
C is
because
also this. C is
yes,
also
sir.
not good. That's true. C alpha B. Nah, that is the condition. Actually, in first case also, C is the main problem here, I think.
Yes, sir. Yes, sir.
C is the main problem.
You
So
don't need to write sir this much.
yeah, one can start in from the C, taking C is a non-zero value and do. That's true. And but okay. Similarly, one can show option three, C and D are false. So let's check the option B only. Okay. So if we do B, then we're done. B will be option. So let's take similarly take A1 B1 element, C is just arbitrary element from the scalar, that means over the field. Then this is equals to T of CA1 plus A2 comma B1 CB1 CB1 plus B2 CB1 plus B2. Then by the formula it is given that CA1 plus A2 plus CB1 plus B2. So one can write this 0 comma C A1 plus B1. Okay, what do you have to write? We have to write C of TA1. Yeah, that's true. C of TA1 plus A2 plus B2. So one can write this as C of 0 comma A1 plus B1 plus 0 comma A2 comma B2, A2 plus B2. Okay, so this is nothing but C of T A1 B1 plus T A2 B2. Therefore, this is the, therefore here T is a vector space. Okay, so option, so sorry, T is a linear transformation. T is a linear transformation. So T is a, to T should satisfy to form a vector space. Yeah, I understand that is I have to form a linear transformation. Transformation T should satisfy this condition. So first question is this. Okay, one question here I just want to give as an I mean your homework, right? Why one should take in the definition of vector space, thus in the definition of linear transformation, what we are taking, let's V and W are two vector space over a field A, over the same field we are considering, okay? And a linear transformation from V to V into W, if it satisfies this condition, then we are saying that that is a linear transformation. A linear transformation is a map which satisfies this condition. Now, question is whether can we consider the V and W, the vector space over the different field, okay? So these questions is very interesting questions. Whether one can take V and W are vector space over the different field over the different field to define a linear transformation. To define linear. This is very interesting question, and this type of questions ask is any interview. Okay, so try to find those type of answers. That will be better to learn in process. Okay, now
Sir, sir, T of alpha, sir,
yes,
T of
huh,
alpha x equal to alpha of tx, then this will not be, sir, defined.
right.
Alpha times tx. If
That's
we
the correct.
take, sir, yes, sir.
Right. I mean, if we can, this will not be well defined. Why it will not be well defined? I mean, not necessarily well defined, but if we, okay, so then if you give the answer of this type of this way, that if it is not well defined, so let's consider to give the well definedness, let's consider the right hand side field is complex number and left hand side field is real number. So in that case, can we define? That case also it will be defined.
Yes, sir.
There
Yes,
will
sir.
also
Yes,
be
sir.
problem. So I mean, no, first question is that can we take the different field? So you are saying that okay, the right hand side, the map will not be well defined in the sense that T of C alpha equal will not be C dot T alpha will not be well defined. That's true. That's very good answer. Now the next question will be, so to make that problem solved, so one can take that left hand side field is real and right hand side field is complex. Still they are different. So can we do that? Because in that case also well definedness is there, right? If we take consider the C from the left hand side field, right? In general, C is taken from the left hand side field because here for the definition of uh, T, so here C is here is need to be open. I mean C alpha plus beta first needs to be well defined. That is well defined. If we take real number, now if we take V, W is the vector space over the field complex number, then C T alpha is also well defined. So in that case, is it possible? That is also not possible. So you can, I think you can will get the
C
answer.
C or C times, sir. Sir, W over R, na, sir.
No,
You
I'm
are
considering V
considering, sir,
over R,
W as subspace.
W over complex number.
Yes, sir. Then, sir, scalar multiplication is well defined, sir.
This scalar
Sir,
multiplication is
but
well
sir,
defined.
this is definition, na, sir.
Yeah,
How can,
definition is there, but I'm just
sir, this is
definition is there.
definition. How can we change it?
No. So in that way, if you say then
Yes, sir.
there is no answer for the first question also, right? So I'm just saying one can start with the definition. Why no one is starting with the definition? Definition is given such a way to study the things in well manner. Okay, so that's why definition. Definition did not came first. First came the things which one to study. First, if anyone wants to study something from their definition comes. So that case also this will be a problem because then you know that the for a linear operator, linear transformation, the image is a vector space, right? Subspace actually. Image is subspace on the right hand side. So when you take the field right hand side field as a super field of the left hand side field, in that case the subspace will not be there. So there will not be I mean, no importance of studying, because this importance of studying is lies on the fact that right range is a subspace, the kernel is a subspace, all those things. Okay, so okay, before these questions, I will just I just want to define the range and null space, so that's why I asked that questions. So now what? Now some fact that range of T, range of a linear transformation T, that is equals to all those W. I mean, we all till now will I mean from now on we will always fix that T is a linear operator from a vector space V to W, both of defined on the on a scalar field A. Okay, this is that W equals to TV such that V is coming from vector space V. This is the thing. This is the set. Range of T is the set. This will form a subspace. This will form a subspace of the W. Okay. So this should be checked. So if we take right hand side field as the superfield of the left hand side field, then this will not be subspace. Now second thing is that null space of T. That is equals to all those element V in the left hand side vector space V. We are here to better to write all those W belongs to the right hand side vector space V such that W equals to TV for some V belongs to capital V. TV is equals to D for some V belongs to capital V. All those V belongs to capital V such that TV is equals to 0, because right hand side the vector space there is a 0. There is no problem with this null space of this. Okay, this will also be a subspace. This will form a subspace of V. One can also easily check. This is very easy check. Okay. Now, now we are considering the range of T is a subspace of V and null space of T is also subspace of V. So there must be dimension similarly, because they are subspace. And if we consider V is a finite, for example, if we consider V is a finite dimensional vector space and W is also finite dimensional vector space, then range T is a subspace of a finite dimensional vector space. So in that case, range T should have a dimension, because range T itself is vector space. Subspace is nothing but a vector space. Similarly, null space is also a subspace of the vector space V. So there would be also be the dimension. So now question is, what is the dimension of that subspaces? Okay, so that is the dimension of range of T is called rank of T, and dimension of null space of T, that is called nullity of T. Okay. Now, fact is that one can consider a vector space T V to W. Now, for example, V is finite dimensional. For example, V is finite dimensional. W, I don't know. W may be finite dimensional, infinite dimensional. That I'm not talking about. Now, if V is finite dimensional, then range of T can't be infinite dimensional. That is clear. And null space of T should be finite dimensional. That is clear, because null space of T is a subspace of V, and V is itself finite dimensional. If we consider V is itself finite dimensional, then null space of T will be also finite dimensional. But if we consider V is infinite dimensional, in that case also range of T can be finite dimensional and null space of T also can be finite dimensional. But in that case, range space and null space both can't be finite dimensional simultaneously. So in that case, there is a very useful theorem. I think, let V be a finite dimensional vector space, then nullity of T, that is null space of T, plus rank of T is equals to dimension of V. If V is finite dimensional, okay, point should be noted. If V is not finite dimensional, we can't say anything like this. For example, one can consider, okay, for infinite dimensional vector space, what one can consider? I think one can consider the space of all functions or space of all polynomials, okay? Space of all polynomials, and T is something px going to, suppose px is a polynomial, that will be something like ai xi x to the power I, ai x to the power I is a I equals to 0 to some finite number n, p is a polynomial. So t on px just getting the first element. So in that case, range is finite dimensional, but null space is not finite dimensional. Range space dimension is 1. So in that case, one can't write this one because it is infinite. Dimension of B in that case infinite. So in that case, there is nothing can't be say like this way. Okay. So this is the theorem. Now let's solve another problem which may be related to this thing. So what it says that let A be the field. Field is the complex number field, and T is a map from F3 to F3. That means T is the map from C3 to C3 with the function defined by this way. Then which of the following statement is correct? What is the statement? The dimension of the range space of T is 1, dimension of null space of T is 2, n element xyz is in the range space of T if it satisfies the condition z equals to x plus y, and element xyz is in the range space of T provided z equals to x minus y. Okay, one can solve a problem by just discarding one by one, but better way to solve a problem is in a single stroke. We have to find a way out in which one can solve a problem in single stroke. Okay, if there is any way at least. For example, for last problem there was no way because you have to check each of them. Okay, but here we have a single stroke way that I will try to discuss. Let t given that t a b c is equals to a plus 2b minus c, comma b plus c plus b plus c, comma a plus b minus 2c. Now now it is asked the dimension of the range space, dimension of the null space, and range space, elements in the range space, nature of the elements in the range space. So we'll try to give answer in singular. Let x y z is in the right hand side field. Okay, f3, f is taken as singular.
Sir, 1 and 2, sir.
1 and 2.
Sir, nullity is 1 and rank is 2.
Nullity 1, range 2. Yeah, that's true. So first option, second option will be discarded. Then how will you, I mean, there is an option one can directly try to, there is two option. I mean, if you try to do it quickly, then there is option that okay, first range nullity if you got, then just you can try to consider this is z and this is x and this is y, and let's check z equals to x minus y or z equals to x plus y. That is okay, but that as I'm saying, I'll try to discuss the problem in such a way that it can be done in single stroke. Okay, that's true. That's whatever that whenever these two will be discarded, automatically there is. I mean, easily one can check the last option. Just to this considering z, this considering x, this considering y. One can check that z equals to x plus y or x minus y. So let's x y z be in the range space of in the range of in the range space of uh, a plus range space of the t. So in that case, then there should exist. Okay, I'll write xyz, it is written. Okay, excellent. So then there exists ABC is taken. What constant I can take? Ti. Then there exists T1, T2, T3 that is coming from the field F, such that uh, T1 A plus 2B minus C. Okay, if xyz equals to j equals to, okay. So sorry. So then in that case A plus, there is no T1. Then what will happen? A plus 2b minus c will be x, and b plus c will be y, and a plus b minus 2c will be z. So one can transform this system of linear equation to a matrix form that is given by this way: 0 1 1 1 1 minus 2, and write it this way: a b c is equals to x y z. Now question is that an element will be in the range space if for this matrix, consider this matrix as A. Okay, in that case augmented matrix is will be like augmented matrix, I think that is called augmented matrix. Yeah, that's true. Augmented matrix, that is 1 2 minus 1 0 1 1 1 1 minus 2, that will with x, y, z. This is the augmented matrix. Okay. Now we have to do the row reduction process, and after row reduction, the number of non-zero row for the matrix A and A full matrix if equal, then we have the solution. So that condition will give everything. So let's do the row reduction process. So first we will do row 3 dashed is equals to row 3 minus row 1. So first keep row 1 as it is.
So please show the sir option C and D, please, sir.
Yes.
Sir, can you show the options again, sir? C and D option.
No, C and D can't be true. Only D will be correct, I
No,
think.
no, sir. I just want to sir, see the options, sir.
Oh,
Okay, sir.
C is the option you
Thank
are
you.
saying. You are saying C is the option, right?
No, 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 sir. I was, sir. I just want to sir, see the
Oh,
options, sir.
oh, options. This is option. Okay, clear?
Oh, yes, sir. Okay, clear.
Okay, yeah. So this will be if we subtract row 3 from subtract row 1 from row 3, what will have? We'll have this minus 2 plus 1, this will be minus 1. Okay, I think I'm doing some mistake. A plus 2b minus c, b plus c, a plus 2b minus 2. Yeah, that's true. Then 1, 2, 1, 2 minus 1, 1, 1, a plus a 1, 1 minus 2. 1, 1 minus 2. So
Sir,
in the
option D is correct, sir.
D is the correct. That is clear from here. That's what I'm saying, sir. You can look at this one is the right hand side is the subtraction of x minus y. That is clear. But I'm just trying to say that let's do something. I mean, in single stroke type of thing. So 1 minus this will be minus 1. Yeah, I know. This is the thing. And what will happen? This will be x, y, and z minus x. Right? This is the thing. Now let's do another row reduction process, that row 3 dashed is equals to row 3 plus row 2. Okay. So then this will be 1, 2 minus 1 x 0, 1, 1. It will be 0, 0, 0 and y z minus x plus y. So this is the situation, right? Now you can look at the rank of the matrix. Now rank of A, or number of non-zero rows. Number of non-zero rows of A, and let's take this is A dash augmented matrix, and number of non-zero rows of A dash will be equal only when z minus x plus y is equals to 0, because number of non-zero row in A is 2, that's clear. Number of non-zero row in A dash will be 2 when this term is 0. So that means z equals to x minus y. So in that case it is clear that the range space, so range space has dimension because number of non-zero row in A is the range space. Why that is the situation? Because I mean, sorry, dimension of the range space of 2. Yeah, so that means, yeah, that also clear from, because the any element is in the range. If that element is x, y, z, then z is in terms of, can be written in terms of x and y. But note that x and y can't be written by in terms of each other. X and y can't be written as a element, some scalar multiples of others. That can't be written, but z can be written. So that's why the dimension of the range space is 2. Then by the previous theorem, that rank nullity theorem, this is nullity of T and rank of T equals to dimension of it. That says the null space of that says, so what this is saying, that this is saying the rank of T, that is 2, nullity of T, that is 1, and x, y, z will be in range if and only if z is equals to x minus y. Okay, this three factor is there, so one can easily discard. So this condition will be there, not there. Dimension of the null space is saying 2, but we have dimension of null space is 1. Dimension of range space of T is 1, but we have that is 2. So this is the only final option. Okay. So yeah, that question is clear, but my point is that try to do in single stroke, because here terms are in such a way that you can easily do subtraction. Easily you can guess from here. Okay, so
Sir,
yeah,
the matrix you got
yeah,
is matrix representation of T with respect to
yes, that is the matrix
standard
representation of
basis.
standard basis. That's true, because that I think that
Yes.
I was thinking
Okay.
to not to discuss today. I mean, why basis thing? Matrix representation I will discuss, but one point is there. I just want to, as
Okay.
you had mentioned, when basis will change, matrix will be changed. So similarly, one can ask, operator is
Yes.
fixed, but if we change the basis, matrix is changing. So does there exist any relation in between matrix for a fixed operator? There is. That will be, I think, discussed in week 4 content maybe. Okay.
Yes,
So
sir.
so so now I will now we'll give a theorem. That theorem is also, I think, sir discussed. Um, I'll just write theorem that says, let V be a vector space over a field F. Let's take V be a finite dimensional vector space. I'll write in short. V be a finite dimensional vector space over a field F. Let I think basis is taken alpha 1, alpha 2, alpha n. Bn, let n be the order, n be the dimension of, let dimension of V is n, and alpha 1, alpha 2, alpha n be an ordered basis of V. Then a linear of, then and W be a vector space over the field. Okay, let V be a finite dimensional vector space. Let W be a vector space. Maybe statement is correct, but not in well arranged. Vector space over the field F. Okay. Then let beta 1 to beta n, any elements in W need not be linearly independent. I mean this beta 1, beta 2, beta n. This element need not be independent. Then there exists a unique linear transformation T from V to W such that T of alpha I is equals to beta I. This is the thing, beta I. So what it is saying, that let's take V and W both are two vector space over the same field F, and V is the finite dimensional vector space with the dimension n. So, and let's consider alpha and alpha to alpha n be the order basis of vector space V. In that case, if we consider beta 1, beta 2, beta n element from W, they need not be linear. I mean, they can be same even. Linearly independent is very big thing, but they can be same even. So in that case, one can give a unique linear transformation T from V to W such that T alpha is equals to beta. How it is in general given. So we know that if we consider a order basis of a vector space V, then for any alpha belongs to the vector space V, alpha can be written as summation of xi alpha I equals to 1 to n, and where xi are coming from the field F. So in that case, one can give a map T alpha. T is linear transformation. So it will respect all the linearity property, and after all the linearity property, one will get T alpha. But what we know, T alpha is actually beta I for all alpha, for all I equals to 1 to all the way n. Okay, so that is equals to summation of I equals to 1 to n xi beta I. So this way one can give the unique linear transformation T. So now on the basis of this, I'll discuss a problem. What it says, this says let T be a transformation from R2 to R3. Okay, V is R2 and and obviously both of them are vector space over the field real R. They are not actually vector space over complex. Okay, and it is given that T of 1 comma 1 is equals to 1 comma 0 comma 2, and T of 2 comma 3, that is equals to 1 comma minus 1 comma 4. Okay, so then it is asked to find T of 8 comma 1. So similarly here alpha 1 can be taken this one, beta 1 can be taken, sorry, alpha 2 can be, alpha 1 can be taken 1 comma 1, alpha 2 can be taken 2 comma 3. Okay, so one can consider alpha 1 is equals to 1 comma 1 and alpha 2 is equals to 2 comma 3 in the above discussion. So for,
Sir,
yes,
sir, domain of T is sir R2.
yeah, domain
Sir,
of 2, there is no
how
problem.
can you
Domain
get the image of 811? This is 811, sir.
811.
This is it written 811.
Yes,
Okay.
this is 811. Not,
Sir,
sorry.
your
I mean, this is small, so
sir
that's why
image
we
is
will.
sir very sir image is very small, sir.
Yeah, I understand. I have to.
Can't
Okay,
see
just
it
just just
properly.
1 minute. 1 minute.
Please sir zoom out, sir. Okay.
I think now it is clear, right? I mean, maybe better than from the
Yes, sir. Yes,
previous
sir.
one. Yeah. Sorry. So now T of 81 it is asked. So similarly, how we have find the solution of T, I mean T alpha. How we have first to write alpha in terms of order basis. Okay. So let's take alpha and alpha to the order basis, but here order basis does not matter. We just need the fixed, I mean factor. I mean fix the element. Okay. So let's take let's consider how one can write 8 comma 11 in terms of 1 comma 1 and 2 comma 3. So here is the best easy way is that one can look at, here is 1 comma 1, here is 2 comma 3, so there is only one extra in the right hand side in alpha 2, and here we have 8 comma 11, so we have three difference, so only that three difference can be obtained from here alpha 2 right hand side from these three. So that's why we will write 3 comma 2 comma 3. So what will the left hand side become is element the 3 to 6. So to get 8 one can write 1 comma 1. I think this is correct. 2 plus 6 8, 2 plus 9 11. Yeah, that's correct. So this is the way. So then one can give the by similar definition t 8 comma is equal to t 1 comma 1 plus 3 t 2 comma 3. But this is 2 1 comma 0 comma 2 plus 3 1 comma minus 1 comma 4. That is equals to 2 0 4 plus 3 minus 3 12. So that will be 3 to 5 minus 3 16. 5 minus 3 16, the first option. So all other option will not be automatically incorrect because there is unique linear transformation. Okay, so all other option will be automatically incorrect. Okay, so this is just a minute. Huh. Okay, so now we'll go to the next questions on the basis of this similar type of questions. So what it is saying, let T be a linear transformation from R2 to R2. Here we are considering R2 to R2, and T11 is the same linear transformation. No, not same, different, because R2 to R2. Then the matrix of A. Okay, so before that, then I should write what is the matrix of a linear transformation. Okay, so what is the matrix of a linear transformation, that I will first discuss. Matrix of a linear transformation. So note that matrix of a linear transformation, in that case T will be linear transformation from a finite dimensional vector space to finite dimensional vector space. If one of them is infinite dimensional, still matrix can be given, but that matrix is not something finite, I mean finite order matrix. That will be something an infinite array. Okay. But whatever matrix till now you have introduced, that is the all finite order matrix. So let V and W are two vector space over the field F. Let alpha 1 till alpha n, let's V the dimension and dimension of v is equals to n, and dimension of w is equals to m. Both of them are integer. Okay, let alpha 1 all the way alpha n, this is I will denote by beta 1, and this b, I mean script b actually, this is not beta, this is script b I'm trying to say, and let beta 1 all the way beta m be the, this is script b, are orthonormal, are not orthonormal, are order basis for v and w. So here v and let eto are some order basis, are some fixed order basis. So here we are considering a order basis of v and w. Okay, so we can change order basis because if for a vector space their order basis also can be changed. Okay, so I'm just right now I'm taking alpha 1 alpha 2 alpha n is an order basis, beta 1 beta 2 beta m is an order basis for v and w respectively. So in that case, so how one will get the matrix? And so now, so let T be from V to W be a linear transformation. Be a linear transformation. Okay, linear transformation. Now consider T of alpha j. Okay, for any, consider for any j equals to 1 all the way n, T of alpha j, that is equals to summation of a, I'll write it at b again, a I j beta I equals to 1 to n. So for all j 1 to n, I am writing T alpha j is an element in W, right? T alpha j is an element in W. So that can be written as a linear combination of the order basis beta 1, beta 2, beta m. So I have written that order basis, and these are the elements from the field F. Okay, because alpha j, that is an element in the vector space V, so T alpha j is an element in the vector space W, so T alpha j can be written as the linear combination of some elements. So here is the thing that I equals to 1 to m aij beta I. Okay, that I am writing. So in that case, yeah, just to verify I have written correctly. Yeah, I think I have written correctly. Yeah, so in that case, then the matrix, then the m by n order matrix A is equals to Aij, that is of m by n order, over the field F, I mean entries are coming from the field F, is called matrix representation of T with respect to beta 1 and beta 2. Okay, that means, and and denoted by T something like beta 1, beta 2, that is the matrix A. And why it is called matrix representation? Okay, why it is called matrix representation? That question is something, why it is called matrix representation. Why it is called matrix representation? The answer is very simple. For any element x belongs to the V, one can write, for any element x belongs to V, one can write that x is equals to summation of xi alpha I equals to 1 to xj alpha j. I'm writing j equals to 1 to n. Okay, that's very natural because alpha 1 alpha 2 alpha n is an order basis. Okay, so one can consider x is equals to something like this way, x1 all the way xn. Okay, this is fixed, I mean this x is expression of x as the x1 x2 xn, that is fixed for the orthonormal basis alpha 1 alpha 2 alpha n. So if orthonormal basis change, then this x expression will be changed. Okay, so now the tx, this tx, what will be the tx? That's the main point. Now tx will be t summation of j equals to 1 to n xj t of alpha j, that will be summation of j equals to 1 to n xj, and that will be I equals to 1 to m a I j beta I. Okay, so now one can write this is as I equals to 1 to m a I j xj. Okay, this is summation j equals to 1 to n a I j xj whole into beta I. Okay, so that means now if we the way we have written x with respect to the order basis alpha and alpha to alpha n as x equals to this column vector, so now one can write tx as a column vector, as a m by n column vector, m by 1 column matrix with respect to the order basis, respect to the order basis b dash, sorry, beta 2. Okay, with respect to the order basis beta 2 one can write, and that will be, and that is something like I'll write j equals to 1 to n a 1j xj all the way j equals to 1 to n a mj xj. This is the matrix. I mean, this is tx with respect to the order basis beta 2. So one can write here x with respect to the order basis beta 1. Okay, this is the thing. So that is, now look at this particular thing is nothing but matrix A and the vector x1, x2, xn. So that's why A is called the matrix representation. So this is the thing. Okay. So now I'll give problem which maybe will be depend on this matrix representation. Okay, now this is the general convention is that whenever the order basis is not given, in that case we have to consider only I mean standard matrix corresponding to the standard order basis. Though I mean it is better to always give the matrix corresponding to which order basis, even it is for standard order basis. So, but here it is not mentioned. I mean, here the question says that let T be a linear transformation given by this way. Then the matrix of A such that Tx equals to Ax, that is the matrix representation, is given by which matrix. But the fact is that here it is want to say that matrix of A with respect to standard order basis. Here A is with respect to the standard order basis. Yeah.
Sir,
Yes.
when we are not considering ordered basis, then the matrix representation of T
Hmm.
will be some A, but then we cannot get Tx is equal to Ax.
Right. Matrix. I mean, if there is not, if you are not considering order basis is there, but we are not giving some order, then there we are not able to write something in this column matrix
Standard
because,
order,
right. No, no. Sorry.
standard order basis. So
No.
standard, if we are not considering the standard order basis, then we will not get Tx is equal to X.
Here we will not get Tx equals to Ax.
Yes, sir.
But if we give order basis, for example, this matrix, this problem here 1 comma 1 comma 2 comma 3. This set will form a basis, right?
Yes, sir.
Now, if you consider this is alpha 1 and this is alpha 2, then this will be an order basis, alpha 1 comma alpha 2. Now, we can give the matrix representation of T with respect to this order basis. I mean, for both left and right hand side with this order basis, right? Also, one can consider left hand side is standard, right hand side is this, or right hand side is standard, left hand side is this. But whenever it is not mentioned, then it is asking to give the answer in standard order basis. Because here I have checked that this will not hold for this order basis alpha and alpha 2. Order basis is not there. I mean, whenever we are giving the matrix representation there, we are just talking about for fixed order basis, not necessarily standard order basis. Now if we consider a vector space which is not like the space of polynomials or not Rn, not complex to the power n, so in that case their standard order basis is not something very, I mean, not known thing, right? In that case, standard order basis is 1 comma 0 0 0 comma 1, like that way, right? So standard order basis is, I mean, availability of standard order basis, that is very limited also, and that is for some known spaces, like known and trivial, I mean, mostly trivial type spaces. So does not, I mean, if linear transformation can have an matrix representation with respect to any order basis, that need not be standard order basis. Okay. I mean, we can just
Sir,
consider any alpha and alpha 2. Yes.
sir, sir, I want to say if Tx is equal to Ax,
Hmm.
then to satisfy this equation, we have to consider, sir, ordered basis, sir. Sorry,
Okay.
standard order basis, sir.
Okay, okay, okay. Yeah, that's true.
Standard.
Maybe that's true. Yeah, that's true. Maybe that's true. Yeah. So in that case, it is asking for in standard analysis. That's I mean, yeah, that's something you can verify in exam hall also. That whether the
Yes.
in which basis you are just. So let's check for the standard error basis. If you consider the matrix in standard error basis, then you will get. Yeah, that's true.
Yes.
So we'll do it in standard order basis also. Okay. So now, first what we'll write, I mean, I just want to know what t1 comma 0 and t0 comma 1, right? So before that, but we don't know t1 comma 0, t0 comma 1. But we know,
Sir,
instead of we
first,
know
sir, express 1 comma 0 in
in
terms of
terms of,
1
right,
1 2 3. Yes.
right, that's true, that's true. So let's write 1 comma 0 in terms of these two vector 1 comma 1 and 2 comma 3. Similarly, one can look at the fact, okay. Similarly, one can, here it will be 12 comma 1 comma 1 to minus 7 comma 2 comma 3. So how to do it? The similar fact is that we have to find, I mean, we have to find 1 on the left hand side. So how one will get? But right hand side should be 0. Okay. No, sorry. Yeah, no, that I have written correctly. Yeah. So that's the reason. So 1 comma n minus 3, 2 comma n. Yeah. So now first, if one wants to get 0 on the right hand side, 0 on the right hand side from these two elements, so this is easily one can check also. I mean, that is not, just write that c1 1 comma 1 plus c2 2 comma 3, that is equals to 1 comma 0, and let's c1 plus c2 is equals to 1, and c1 plus 3 c2 is equals to 0. So one can subtract and get c2 is equals to 1, c2 is equals to 1. So sorry, c1 comma c1 comma c1, and c1 plus 2 c2 t c3 is equals to 0, right? So c2 is equals to 1. I want to find 1 comma 0. What are the two? 1 comma 1, 2 comma 3, right? 1 comma 1, 2 comma c1 plus 2 c2, that is 1. C1 plus 3 c2, that is 0. Let's subtract the second equation from c2 is equals to, oh, c2 is equals to, what I'm doing, subtract from here to here. So c2 is equals to minus 1.
Sir, beta will be minus 1 and sir, alpha is equal to 3, sir.
I
Yes,
think
C1 is equal to, sir, 3, C2 is
ah,
equal to minus 1. Yes, sir.
C2 equals to minus 1 and C2 will be 3, I think. Then,
Yes, sir. Yes, sir.
so 1 minus 1 need not be written. So 3, let's write 3. 3 minus 2, that is 1. 3 minus 3, yeah, that's 2. That's true. I don't
Yes,
know.
sir.
So now 0 comma 1. So similarly, one can write here 0 and here 1. So what we will get, that C2 is equals to 1. So automatically, if we write C2 equals to 1, C1 will be 1 minus 3, that will be minus 2, right? So C1 will be minus 2, 1 comma 1
1.
plus
1
2
times
comma
2 comma 3. Yes, sir.
huh. So let's check. Yeah, this is 0 and yeah, this is correct. So now what I have to find, that t of 1 comma 0. Sorry, this is not t. This is just a t of 1 comma 0. That will be easily t of 1 comma 1 minus t of 2 comma 3. But we know t of 1 comma 1 is 3 1 comma minus 2, minus t of 3 is equals to minus 2 comma 5. So this 3 plus 2, that will be 5, and 3 to minus 6 plus minus 5 will be minus 11.
Yes,
Okay,
sir.
and t of 0 comma 1, that will be similarly minus 2 of t 1 comma 1, that will be similarly, I'm just not writing that much, 1 comma minus 2 plus 2 comma 3 will be minus 2 comma 5, that will be this is something rough, okay, this is not included, minus 2 minus 4 and 2 to 4 minus 5 minus 1. So does there exist this solution? 5 11 minus 4 9 minus for 9 it is. Okay, 9. Yeah, that's true. 9. I've just written correctly. Minus for 9. Minus 2 plus 4 and yeah, 9. So the answer will be, so therefore t with respect to the order basis, the matrix of t with respect to the standard order basis. So
5
mat
minus 4 minus 11 minus 9.
right.
9.
Matrix of t with respect to the standard ordered basis is 5 minus 11, that is the first column corresponding to the first vector, minus 4 9, that is the second vector, right? So this is the minus 4 9, right? Minus 4 9, yeah. So this is not correct, all other automatically not correct. Okay, yeah. Now I will give the same some questions, 1 2 3 4 5. So this is the
So
question,
please
what is,
zoom in. The zoom
oh,
in.
okay. I think this is fine, right?
Yes.
Yeah. So what we said, let V be the vector space of polynomial functions of degree less than equals to n. Therefore, the vector space will have dimension n plus 1. Okay, over the field F, and let T be the linear transformation from V to R, given by T of Px equals to sum of all coefficients of Px and Px belongs to V. Then which of the following is correct? So let's consider the vector space V, that is equals to summation of ai x to the power I equals to 1 to n, such that I equals to 0 to n, such that ai is belongs to the field over the field f, and xi is there, that is the space of all polynomials, that is space of all polynomials of degree less than equals to n. Okay, so ai can be 0 also, but yeah. So now let's tpx is the element for any px, Okay, note that dimension of v is equals to n plus 1. Okay, now for any px is equals to summation of I equals to 0 to n ai x to the power I belongs to v. T of px by definition is given by summation of I equals to 0 to n, right? So in that case, it is
Sir,
clear.
option D.
Yeah, option D will be correct, and
Last
all other
option
option
should
will
be the
be,
correct.
yeah,
Yes.
all other option will be discarded. But we'll just discuss a little bit of nullity of T is n minus 1. That's not false. That's false, because as we know, the rank of the operator T plus nullity of T nullity of T is equals to dimension of V, and here dimension of range of T is equals to 1. That's clear, because that is always going to the scalar element. So that's why right hand side does not needs any other element. So that is dimension 1. And also the T is defined from V to R. So automatically that can't be, range can't be more than 1. Okay. So that is rank is 2. So that imply rank of T is actually, sorry, rank of T is 1. So in that case, that is equals to n. So nullity of T is equals to n, that implies the dimension of null space of T is equals to n minus 1. Sorry, sorry, this is n plus 1, n plus 1, that will be n. So first, so this option is false. Nullity of t is 1, that is also false. That not need not, I mean, need not be true, because if we consider n is 1, in that case, nullity of t is 1, right? Just considering the polynomials of degree less than equals to 1. Those are actually linear polynomials. Those are called linear polynomials, but that is not necessarily true, because n can be taken any number, right? So now the basis of the null space of T is this, because this is also false, because T of, note that option C is false, as T of x to the power I is not equals to 0. They are not 0, right? Because just they are, I mean, they are always, T of xi is equals to always 1. That is 1. That is not equals to 0 for all I equals to 1 to n. So therefore, the elements are not, this is not null space. Then the set x square x to the power n is not in null space. But one can easily check these elements are in the null space, because for this element the sum of the coefficient is 0 always. But easily one can check the last option. Easily one can check any elements in x minus 1, x square minus 1, x to the power n minus 1 is in the null space of T, right? But null space of the dimension of the null space of T is n, and here we have total n number of elements. So they are elements in the null space of T. But to show that this is a basis for the null space, now to show this set x minus 1 comma x square minus 1 all the way xn minus 1 is a basis of the null space of T, we need to show that this set is linearly independent. So that this set linearly independent. So let's check this is linearly independent or not. So let's let C1 or Ci x to the power I minus 1 summation of I equals to 1 to n, that is equals to 0. That implies that summation of I equals to 1 to n Ci x to the power I minus C1 plus C2 plus all the way Cn is equals to 0. But the set 1 x square all the way x to the power n is linearly independent. So linearly independent. Therefore, what we will have, C1 is equals to 0 is equals to all the way C2 is equals to Cn, and C1 plus C2 plus all the way Cn, that will also be 0. So that is, so therefore the set, therefore x minus 1, x square minus 1 all the way xn minus 1 is linearly independent. Okay, linearly independent, and consequently this is basis of the null space of T, right? Yeah. So now, so this is very clear, but just to fact check, verify, because whenever you will encounter in competitive exam, so there most of the questions will be in such a way that for each options you have to give, and I mean have proper reason. Okay. I mean nowadays exams are becoming tough, so better to have all, I mean. So now, okay, this is what I think we have done. Yeah, this is we're done. Sorry. Now we'll give C. Right. These questions we'll discuss. I'll just okay. Lots. Yeah. I think now it is. Yeah. So now what says that let V be the vector space of polynomials functions of degree less than equals to 3 and field F, and let T be a linear transformation from V to R3 given by this way T Px is equals to P1 P minus 1. So T of, so V is the vector space of, V is the vector space of all polynomials like ai x to the power I equals to 0 to 3. Okay, ai coming from the field A. Okay, so dimension of the vector space V, that will be obviously 4. Okay, now let's T of, for any px in the vector space, for any px in V, T of px, that will be p of 1 comma p of minus 1 comma p of 0, right? This is the tuple that is inside R3, right? R3. So now what is saying that then which of the following statement is correct? T is 1 1 or not? T is range of T, range space of T is R2. The null space of T is span x3 minus 1, and the null space of T is x3 minus x. So let's first check T is 1 to 1 not. Okay, okay. So let's give a definition. I will not write. So a linear operator T from V to W is said to be. That means here V and W both are on the vector space over the same field. Said to be, but need not be finite dimensional. Said to be 1 1 1 1 or non-singular if and only if it satisfies any one of the condition. If and only if it satisfy any one of the following conditions. What are the following conditions? So first condition is that T of alpha is equals to 0 for some alpha belongs to V implies that alpha is equals to 0. That is same thing says that T of alpha 1 equals to T of alpha 2 for some alpha 1 alpha 2 belongs to V. That implies that T alpha 1 equals to alpha 2. And third condition is that T map a linearly independent set of V onto a linearly independent set of linearly independent T maps any linearly independent set. So there one can write two more condition. Set of any linearly independent set to a linearly set of W. Okay, so three condition I'm just saying. T is non-singular or injective. If and only if T of alpha equals to 0 implies that alpha equals to 0. That is, I mean, directly similar to the fact that T alpha 1 equals to T alpha 2 implies that alpha 1 equals to alpha 2. But the third says that T should maps every linear independent set on the left hand side V to the linear independent set on the right hand side. So that is equivalent to the fact that T is injective. So we will be only consider this first condition only. Okay, so these conditions are all equivalent to each other. Okay, I will not discuss how they are equivalent. So let's check whether T is injective or not. So to show T is injective, we have to show that T of alpha equals to 0 implies that alpha equals to 0. But if we want to show that T is not injective, then what we have to show that there exists a vector alpha in the vector space V, which is non-zero, for which T of alpha is equals to 0. So let's take Px is equals to x minus 1. Okay, T or Tx equals to x minus 1. Then, okay, I want to show that something that is not 0, x into x minus 1, x plus 1. Then T of Px, that is equals to by definition P of 1, P of minus 1, P of 0. So let's that this is an element in the degree 3. Okay, this is the element of degree 3, but we can't take more than degree 3. Okay, but we can take degree 3. So now p of 1 equals to 0 clearly, because here is x minus 1 factor. And second is that p of minus 1 is 0 because here is the x plus 1 factor. And p of 0 is 0 because here we have x 0 factor. So this is 0, but p of x is not equals to 0 in V. Therefore t is not 1 1. Okay, but one also we can see that this vector, also note that this vector x minus 1 x plus 1, that is equals to x cube minus x, is in the null space of, is in the null space of T, right? But what is the other option? So this option automatically cancel out. So range space of T is r square or not? Sorry, this will be r cube. This will be r cube. This is false. Okay, r cube or not. So we will check that this is r cube. So how to do this? So we have to consider each polynomial separately. So let's first consider px.
Storage q minus x will span the null space, sir.
Yes, 2
X cube
minus.
minus x will
Yes, yes,
x
yes.
cube minus x will
Will
yes.
span will, but that will be the, okay. Why this will be only, why this will be only if we can show that range of T is, I mean range of T is R3, three-dimensional space, right? So in that case, what we are seeing here, T is operator from V to W, right? V is a vector space of dimension 4 and W is a vector space of dimension 3. So in that case, if we can show that range of T is actually three-dimensional space, so by rank-nullity theorem, the null space should have be one-dimensional. But here we have a single element corresponding to the null space. So that will be the null space. That will generate the null space. There is no other element, right?
Yes.
Yeah. So we'll show that the range of T is three dimensional, full, generates full R3. So now let's first consider, let px is equals to 1 by 2 x into x plus 1. Then by definition, T of px, that will be first p1. What is p1? That is 1. P of minus 1, that will be 0, and p of 0 will be 0. And similarly, p of x is equals to, when p of x is equals to, similarly 1 by 2 x into x minus 1, 1 by 2 is needed, yeah. Then t of px, that will be, if we write p of 1, that will be 0, p of minus 1, that will be 1, and p of 0, that will be 0. So and when p of x, that is equals to x minus 1 x plus 1, so in that case p of px is equals to, p of 1 is 0, p of minus 1 is 0, and p of 0 is actually minus 1, so better to write minus 1, so this will be plus 1, plus 1. So in that case, so what we have seen is that the range of t contains this set 1 comma 0 comma 0, 0 comma 1 comma 0, 0 comma 0 comma 1. But we know that the range space of T is actually a subspace, and also these are the, this particular set 1 comma 0 comma 0, 0 comma 1 comma 0, and 0 0 1. This forms a standard order basis for the rank 3 space. This is a standard order basis for R3. Therefore, T is on 2. Okay, so this will automatically give the range space of T is R2. Okay, sorry, range space of T is R2. So this is false. This is false. Range space of T is R2. That is false. Null space of T spans this one. That is also false. This will be the correct option. Okay. So there, this implies that x cube minus x is the null space of, or that is linear span, is the null space of T, and this option C is false, as x3 minus 1 is not in the null space of T. That is clear, because T of, here if we write T of minus 1, then it will be minus 2. So that means this is, or even T of 0, that is minus 1. So that is not in null space of T. Check this. This is very easy, just to place the thing. Check. Okay. Now I'll consider other problem. Okay. Okay, but before this, I should have discussed the what is invertibility and algebra thing. What invertibility and algebra thing says is that let T from V to W be a vector space. So before that, let V and W are two finite dimensional vector space. But to define in inverse, we don't need actually finite dimensional. But okay, so let's write T be a vector space. Vector space. Let T be a vector space. Sorry, the T be a. I mean V and W are vector space over the same field. T be a linear transformation. Linear transformation. Then T is said to be invertible. Said to be invertible if there exists a linear operator denoted by T inverse from W to V such that T inverse is equals to identity operator on W and T inverse T, that is identity operator, identity linear transformation from V. This is identity linear transformation, identity linear transformation on W, and this is identity linear transformation on V. That means they are actually identity map, nothing special. Okay, so in that case, then T inverse. So T will be invertible if there exists a linear operator T inverse from W to V such that T inverse equals to identity on W and T inverse T is identity on V. And in then T inverse is called the inverse of T. Okay. Now, if V is finite dimensional vector space, in that case, T, okay, in any case, T will be invertible if and only if T is injective and 1, 1. T will be invertible if and only if T is injective, sorry, 1, 1 and is same thing, just whatever term we are using that will use. T is 1, 1 and on 2. Okay, in that case we'll write T is if V is a vector space, if V is okay, but this is maybe not true for every vector. V be a finite dimension. Let me just let me just check once, because if V is not finite dimensional vector space, in that case there may be some problem. I mean, 1, 1 and on 2 will be little problematic. I mean, without 1, 1 and on 2,
Sir, this is general condition, na sir,
yeah,
for
no,
any
no,
map.
this is general condition that this is general condition for invertibility. So here is also, but here is one fact that inverse should be also linear operator, right?
Sir, in finite dimensional spaces, if we are able to show that T is 1, 1, then it is automatically, sir, on 2.
No, 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 no. Why it will be? Suppose we are
If,
defining map from R2
sir,
to R3,
sir,
right?
no,
Right.
sir. Sir, if these sir, dimensions are same, sir, domain and
Obviously, V
dimension
and
and
W
domain
are
and
same.
code.
So in that case, one gives on two gives one, and both each of singleton.
In
But
this case, sir, dimensions in finite dimensional spaces, the dimensions should be same, sir.
yes,
Then
that's
in
true.
that case only, sir, they will be, sir, 1, 1. There will be, sir, invertible linear transformation, sir.
I mean, one will give that I mean, one will give that other one on two, and each of
Yes, sir.
single. I mean, individually each will give that the
Yes, sir. Yes,
um,
sir.
invertibility. But I just want to confirm the fact that T is, I mean, if V is not finite dimensional, W is also not finite dimensional. In that case, T is invertible if and only if there is a, oh yeah, that's true. Without any even V need not be even finite dimensional. That's true. Using the T from beta is called invertible, there is a function but identity such that and if T is invertible, then the function is consequence. T is invertible if and only yeah. Irrespective of the fact that T is 1 1 and T is on 2, that will give, I mean these two 1 1 and on 2 will give invertibility. But if V is finite dimensional and W is finite dimensional, in that case both side
Sir,
range ran, yeah.
sir, if T is sir invertible, suppose sir,
Hmm.
I'm not saying that T is inverse is linear operator. Sir. T is if T is linear operator and inverse of T exists,
Yes.
then T inverse must be sir linear operator.
Linear operator. But yeah, that's true. Whenever we are defining a linear map from T from, but what inverse? Why inverse should be unique? First of all, that is the one thing. No, I'm just saying that suppose we have given a map function v to w. So in that case, f is linear. That's okay. Suppose f has an inverse g that is equals to identity map on v map. I'm just considering as map. Gf is equals to identity map on w. So in that case, the g is unique. I think that will give the yeah g is when g is map, then that will be unique. So in that case, t will be inverse. T inverse will be linearly independent. Sorry, linear transformation. That's true. If T is invertible, but definition is something says that linear operator, because why considering linear operator, when we try to find the inverse of an element, so that inverse should be on that set itself. So whenever we are trying to find the inverse of a linear operator, so that means we are actually finding it as a linear operator. I mean, my point is that suppose we are considering the set of all real number from 1 to infinity. So if and considering the multiplication operation on there, right? So now if I consider an element A, what is the so multiplication with multiplication, what is the identity? Identity is 1. Multiply 1, I'll get A. So my point is that if I want to get the inverse of A, then that will be 1 by A, right? But 1 by A is not in 1 to infinity. So I mean, whenever someone wants to find an inverse or something, that means that element should be inverse also should be on that set itself. But here it is saying that if there exists a map T inverse such that which satisfy this condition, only this condition, then that will be linear.
Sir,
That is
we
what
are
he was saying.
not sir, considering that sir group sir.
Yes.
We are not finding sir, sir. We are not finding inverse in a group sir.
No, but we are finding inverse in the space of linear operators also, right?
Where it is sir, said
No, no,
sir.
actually, actually there is a thing that lets V and W be the vector space, set of all linear operator from V to W that forms a vector space. Whenever we take an element from there, so there we are defining a multiplication here, right? T dot T inverse. That is
Hmm.
multiplication. With that
With respect to
multiplication,
composition sir.
right. With that multiplication, we are finding inverse. Actually, we are finding inverse, but in group case, every element should have inverse. But here, need not be in should have inverse always. Right. We can get an linear operator which is not 1 1 or not on 2. That is not invertible. There is no inverse. But if inverse is there, so that should be linear. So there is group structure. There is not group structure. There is a composition which is playing the role of multiplication in the algebra. In an algebra, this L comma B, L V comma W, that will form an algebra. Okay, that will I will not go. But yeah, main point is that if there exists an transformation, there exists an function which satisfies this condition. This L T inverse equals to I W T inverse T I V, then that will be what is called linear. So now where it is saying that let T be a linear operator from R3 to R3 itself, R3 to R3, and T is given by this way. So question is that whether inverse of T does exist or not, and if exists, then what of them does so whether inverse exists or not. If inverse exists, first condition is automatically false. So after that we have to find the inverse, and inverse will be unique also. Yeah, here we have not said unique, the invertible, if there exists linear operator, but that linear operator will be unique also. That is in general inverse always happens. Okay, so let's t is given by this way, t of x1, x2,
Sir, let
x3.
us try it first, sir.
Yeah,
Sir,
which one?
sir, wait first, sir. Sir, we want to try first.
Okay, you can do it. Little bit. Yeah, I'll give
Wait for
3 4
submit.
minutes.
Yes.
Ha ha ha. No problem. You can do it. No problem. First check. Yeah, one stroke check will be there also. That is also possible. So this is actually. I'll not do just writing the things. 2x2 plus x3. This is,
Sir, it is invertible, sir.
yeah, it is invertible. That's true. So now let's find inverse. It is invertible. So one option will be, so inverse when it is invertible and when we have very less number of elements, so one can easily find inverse. So basically, what if it is invertible? Suppose this is the inverse x, y, z. So what we have to find? We have to find x1 in terms of x, y, z, and x2 in terms of x, y, z, and x3 that will be in terms of x, y, z, right? So that is written in z1, z2, z3. Let's suppose this is equals to z1, z2, z3. So we have to find T inverse z1, z2, z3 in terms of z1, z2, z3. So let's do it in single stroke, which will give the invertibility as well as everything. So one can write. So what we have, 2x1 plus x2 plus x3, that is equals to z1, 2x2, 2x2 plus x3, that is equals to z2. One can easily check here, because here it is saying that x1 plus z2 is equals to z1. One can easily check something here. So whenever, if you just quick check, you have to find patterns, some easy patterns. Minus 2x1 plus x3, that is equals to z3. So this will be transformed to the system of linear equation 1 0 2 1 minus 2 0 1. I'll just this one, and with I'll this one with the vector x1, x2, x3, that should be equals to z1, z2, z3. So let's consider this is the matrix A, and let's A dash is equals to the similarly 1 2 1 0 2 1 minus 2 0 1, as well as z1, z2, z3. This is the thing. Okay, so now we'll do the row reduction process. Okay, that row reduction process will give everything. Yeah. So first step, row reduction process of the first step, that I'll write R3 dash is equals to R3 plus 2R1. So what will happen? First one will be there as it is. Second I am keeping as it is. The third one is the multiplying row 1 with the 2 and adding with this. So this will be 4 and this will be 3 and this will be Z3 plus 2 Z1, right? This is the thing. So let's do another one. So write it as row 3 dash is equals to row 3 minus row 2 row 2. Okay, so first row is, it is as it is, 0 2 1 z1 z2 0, 4 minus 4 is 0, and 3 minus 2 is 1, Z3 plus Z3 plus 2Z1 2Z2. This is the thing. So now one can easily look at the number of non-zero entries in A is same, that is 3. So then number of non-zero entries in A dash, that will also be 3. There is no doubt about that. Okay, so that means this system has solution. But so okay, as number of non-zero rows of A and A dash are same, and that is 3, then as both of the 3, then T is injective or 1 1, right? If for example that is 2, in that case that is, if that is 2, then rank of the T, I mean dimension of the range space will be 2. So in that case nullity of T will be 1. In that case T will not be invertible, but here it is 3. So range is actually, dimension of range is 3. So T is 1 1 and on 2, both of them 1 1 and on 2, because here map is given from R3 to R3. So one happening, I mean if it is range is 3 dimensional, so in that case T is the on 2 and automatically T is 1 1. So therefore T is invertible. So how to find inverse? We'll do it quickly. So what this system of linear equation transform to this after row reduction. So that means, so therefore therefore after row reduction, system becomes x1 plus 2x2 plus 3x3 is equal to z1. Sorry, x1 plus 2x2 plus x3 is equal to z1. 2x2 plus x3 is equal to z2. 2x2 plus x3 is equals to z2, and x3 is equals to z3 plus 2z1 minus z3. x3 is equals to z3 plus 2z1 minus 2z2. So x3 is this. So whenever x3 is this, so this will give that x1 is equals to z1 minus 2x2 plus x3, that is z2. Z1 minus Z2, that's clear. Now we have to find x2. 2x2 is equals to Z2 minus x3. So x2 is equals to 1 by 2 Z2 minus Z3. x2 minus x3. So x2 is 1 by 2 Z2 minus Z3 x3 Z3 minus 2Z1 plus 2Z2. Okay. So therefore it will be 1 by 2 3Z2 minus, okay, I'll write in order, T2Z1 plus 3Z2 minus Z3. So what we'll have, x1, x2, x3. In terms of Z1, Z2, Z3, what we are getting, x1 is equals to Z3, x1 is equals to Z1 minus Z2, x3 is equals to 1 by 2, 2Z1 minus plus 3Z2 minus Z3, and x3 is equals to Z3 plus 2Z1 minus 2Z2. So this is the thing. So one can easily check. I think this is the option. So all other options automatically cancel out, right? So this is, I mean, one can easily solve this problem without doing all these things. Okay, that's true. That one can easily just by observe and little bit of short calculation one can do and get the answer. Main point is that I just want to give the short systematic steps, so that if the problem is not I mean not, I mean involved with many things, so in that case you can get the solution. So now,
Sir, can you please show the last slide?
yeah, this one, or okay, just 1 minute. I think there is a network issue
Yes,
from
sir.
my side. I think it is visible to you.
Yes, sir.
uh,
Okay, sir. Thank you.
uh. So now I'll give another problem, but before that I'll just read the product of two linear operator. That is already I have said, but just tell you product of two linear operator. Okay, no, not before that. We will give a solution on problem, and after that we will give product. Yeah, yeah. What it is saying? Let T be a linear transformation with T100, T00. Okay, this is very easy. I think I think one can easily check. There is nothing big deal here. 1 comma 1 comma 2 is equals to, it will be 1 T 1 comma 0 plus 1 T 1 will not be written. 1 will not be written. 0 comma 1 comma 0 plus T2 of 0 comma 0 comma 1, right? That's clear because that is from linear transformation. One can T is linear transformation, so by linearity one will get this 1 comma 1 comma 2. That's true. So therefore it will be 0 comma 2 comma 1 plus 1 comma minus 1 comma 2 plus 7 comma 2 of 7 comma 2 comma 4. Therefore it will be 0 plus 1 1 plus 7 to 15. Okay, next is 2 minus 1, that is 1 plus uh, 4, that is 5. Next is 1 plus 2, that is 3 plus 4 and 2, 8, 8, 3.
Sir, this is easy, sir.
Yeah, this
Don't
is
waste
easy.
time, sir.
Yeah, I think I mean, this is very much direct. You can I think, yeah, better, it's easy. I will not do it. Okay. I will not do it. This is just to checking and nothing special.
Sir, calculations.
Yeah, just calculation. Check. Easy one. Okay, so I'll go to the next. Okay, so before going to the next, so I'll just give only single, I mean, little bit of just formal definition. Product of or multiplication, not multiplication is not the good term. Product of product whenever we see scalar, yeah, product it is product of two linear operator. Okay, how to do it? Let V and W are two vector space over the same field.
Sir, composition is a good word, sir.
Yeah, composition is the product here.
Sir,
So,
the
okay,
product is a different thing, sir.
I understand. I understand. Yeah, that, I mean, scalar product. When we say scalar product, that is also product. It is saying. I mean, that is also but here I just want to take then the, as there is confusion, then I'll take the what term some standard books following that term I'll give. I'll take that is in there is a section, I think, algebra, that is what it is saying. Composition is the, I think, better word. That's true. That's true. Composition is a better word. Huh. We see that the composition using linear operator with this multiplication. Multiplication depend on its if by k. Multiplication of two table operator. That will be the term. That will be in quoted term. So that is the composition. That's true. But composition, because what is the problem with the multiplication and composition? I just want to say this one. Here it will be, for example, we have two function f and g. Linear operator is also function, right? We can give product or multiplication f dot g by two way. That is f compose g or f dot g, means that f compose g is the f composition g. That is, suppose I just want to obtain value at x, that is f of g of x. That way one can write. But one also can give f of x, g of x. But here, as we are dealing with vector space, so two vector, there is no product of two vector. We don't know how to do the product of two vector in general. So that's why that multiplication is only one option left, that is the composition. But there are also functions. So in that case, if we just want to say, so product means multiplication term one can give. Composition need not be always multiplication. That's the my point. Whenever multiplication given on a algebraic structure, so in that case composition is not always the multiplication. In vector space it is always. That's true. So let T and let V and W be two. Let's look. All right, V and W are two vector space over the same field. Okay, here I think V will be V. V be a vector space over field A. When you do composition, okay, if we have let's VWZ, then let's take let VWZ are three vector space over the same field over the same field F, and let's T from V to W and U from W to Z are two linear operator, then U dot T that is from G to Z defined by U dot T at a vector x is equals to U of Tx will also be a linear operator. So one can check, that is very easy check, that this will be from a linear operator. That linear operator needs to be checked. That is called the multiplication or so here. So this is the composition. So this is the called multiplication of two linear operator. Multiplication of two linear operator, which is composition in this case. So we'll use some problem for this actually. I think this is the problem. Okay, we have given last, yeah. This is the problem. Just this is something. So this is the problem. What problem first says? Let's read carefully. Let's T and U are two linear operator. T with the linear operator. T maps T x1, x2, x3, x4 that goes to 0, x1, x2, 0. So this T is not only making some elements 0, but it is also shifting some elements, okay? And U is another operator that is given by U x1, x2, x3, x4 that is equals to x3, x4, 0, comma 0, okay? So let range of T, TU and UT denoted by RTU and RUT respectively. What is the null space of TU and UT are denoted by NTU, NUT respectively. Then question is which one of the following statement is correct. So as it is written each, so there will be only one option. So when you get the correct option, you can leave the problem. But I'll here discard all the things. Okay, so let's first find what is TU, UT, and then what is range T, range of UT, and null space of UT, all these things. Okay, so first find TU. TU on the element x1, x2, x3, x4, that will be T of U x1, x2, x3, x4 will be x3, x4, 0, comma 0. So now this is new x1, x2, x3, x4. This is new x1, x2, x3, x4. Now what it will happen? Just it will shift the first two element. T actually does the first two elements shift to the middle and makes all other into 0, right? So in that way, so shift the first two element in middle and write the this way, right? This is the TU. So now, therefore, range of TU, what is that? That is equals to range of TU, that is written, that is equals to all the entry written by this way, such that X and Y all are coming from the field R. Yeah, X and Y are all element in R. So this is an subset of R to the power 4, but range of TU. And null space of TU, null space of TU that is given by NTU that is equals to all those element x1, x2,
Zero you
x3.
have 3, x4.
Yes. Sorry.
Sir, 0, 0, x 0, 0, x3, x4. The
0
general
0.
element of nullity of T, sir.
Oh, nullity. Oh, sorry. Yeah, sorry, sorry. Yeah, maybe that's true. Maybe that's true. I'll just check. Belongs to R4 such that 0 comma x3 comma x4 comma 0 will be 0, right? 0 is the here, 0 is the full thing. So that means element will be like x1, x comma y. I'm writing x comma y form. Okay, sorry, x3, x4. Sorry, I'm just messing up some things. Range of t is this. So null space. If I write, okay, x comma y, 0 comma 0, x comma y, right? Something like this. This element will be right. You are saying this one, right?
Yes,
Yeah,
yes, sir.
that's true. That's true. Okay. So this is the null space of T. So first condition that rank of TU is 1, that is false because this is the rank of TU is 2. Clear? So first is false. Nullity of TU is 3, that is also false. So therefore,
Sir,
yes,
sir, here null space of Tu is sir x given by sir x comma y comma 0 0. Sir, because x3 will be 0 and x4 will be 0, sir.
yes.
If you
Oh, sorry,
compare,
x comma y.
so
X comma y,
yes, sir,
right?
x comma
X
y
comma y.
comma 0 0.
Yeah,
Yes, sir.
that is what I just messing up. Yeah. So element will be x comma y 0 comma 0, right? Yeah, just
Yes, sir.
x comma y 0 comma 0. Yeah, that's true. That's true. Thanks. So, but nullity of tu will be 2 here because there is 2 clearly. This space has dimension
Yes,
2, this space has dimension 2, so automatically first two condition getting cancelled out. But to get the next two condition, I just need to find. So now first condition one can check this condition dimension of tu and dimension of rtu intersection ntu. So now rtu intersection ntu, what will be that? Note that here is the second and third element is non-zero. Here is the first and second element is non-zero. So that will be all element like 0 comma x comma 0 comma 0. X belongs to R. Okay. So therefore dimension of range tu intersection null space of tu, that will be 1. Okay. So that does not, so that is also cancel out the third condition. So automatically this condition will be correct, but will check properly. Okay. So okay, so one can easily check. I'll just write the ut, then that will be better. So ut x1 x2 x3, there is not much time, so I'll try to quickly write uh, x1 x2 x3 first. T x1 x2 x3 x4 will be 0 comma x comma 0 comma x1 comma x2 comma 0, and next it is just shifting things x3 x4 x2 comma 0 comma 0 comma 0. I think this is the thing. So therefore range of ut, that is equals to all the entry x comma 0 comma 0 such that x belongs to R, and null space of ut, that will be x1 x3 x4 will be 0, so
Sir,
that will
2
be
will
0
be
comma x
0.
comma 0. Sorry, 0 comma x comma, sorry, except x2 all other entry will be there, 0 comma y comma z, right? Such that x is belongs to x y z, but all elements are coming from x y z, all elements coming from the real number, right? So therefore range space of ut intersection null space of ut, that will be only the element of this form 0 comma 0 such that x belongs to R. So therefore dimension of range of ut intersection of null space of ut, that will be 1. Okay, so last option automatically correct. I'll just check. Yeah, that's true. Now we'll give the last problem, then after that we'll end this session. Okay, this is also something verification. We'll do little bit of what it says. Let T V be a vector space of for all four tuples over F and T by linear operator on it such that rank of T is equals to this. Then T is okay. So you have to check one by one. I'll check two. If after time permits, I'll discuss all other. Okay. So let's first one. So first one says that a T of x1 x2 x3 x4, that is just doing x1 switching x3 and x2 and making it 0 on the right hand side. So now t square of x1, x2, x3, x4, that is equals to t of x1, x3, x4 comma 0. So in that case, now what will happen? X1 will be as it is. Okay, switch, sorry, here it is x3, x2, x2. Switching x2, x3 and making it 0. So this is the thing, right? Okay, so x2, x3, this is the thing. So now, so first case, rank of t. So in this case, rank of t is equals to 3. Rank of t square, that is equals to 3. So whether 3 equals to 3 times 3 by 2, that is not true. So that's why option A is false, right? Now option B. Option B says that let T x1, x2, x3, x4, that is equals to x4. x4 is coming in this side and switching x3, x2 and making it 0. So now t square of x1, x2, x3, x4, that is equals to t of x4, x3, x2, comma 0. So now what is the rule? Switching in between, that will be x2 comma x3, and taking the right hand term here, and x4 is vanishing. This is the thing. Okay, so in that case, rank of t is equals to 3 and rank of t square, that is equals to 2. So whether 3 equals to 3 by 2 times 2, yeah, that's true, that's true. So that's why B is correct. B is correct. So let's similarly one can check. I'll just check one more because we have time here. I think 3-4 minutes I can also go ahead. Yeah, 3-4 minutes I can go ahead. Okay, so it's option C. Option C says T of, this is the condition. Rank T equals to 3 by 2 rank of T square. So T x1, x2, x3, x4, x2 0, x4 x3. T of x1, x2, x3, x4, that will be x2 0, x4 x3, right? X4 x3, yeah, x4 x3. So in that case, so t square of x1, x2, x3, x4, that will be t of x2 0, x4 x3. So this is the new one, y1, y2, y3, y4. So this will be y2 comma 0 comma y4 comma y3. So So, right? So what is y2 here? Y2 is 0 here, and sorry, huh, huh, y2 here is 0, and 0 is there automatically. Y4 is actually x3, and y3 is actually x4. This is the thing. So in this case also, rank of 3, rank of rank of t, that is equals to 3, and rank of t square, that is equals to 2. So 3 is equals to 3 by 2 into 2. So 3 here. This is also correct. So option here is, I think if you are correct, so is or are false. Yeah, there is two option I remember. Yeah. So therefore, uh, so this will not be. This is just for verification. So we'll write above. So this will be 0, 0, x3, x4. So therefore C is correct. So let's check D. What D says, T x1, x2, x3, that is equals to, that will be 0, x2, x3, x4. Okay, just to making first term 0. So clearly it is very easy, x4. So therefore t square x1, x2, x3, x4, that will be t 0, comma x2, comma x3, comma x4. That will be again 0, comma x2, comma x3, comma x4. So therefore rank of t, that is equals to 3, and the rank of t square, that is equals to 3. So here 3 is not equals to 3 by 2 times 3, right? That is not true. So therefore D is not correct. Yeah. So only option is B and C. So B and C is correct, and all other two options will be false. So this is all. So if you have any other problem, I mean, this is just easy verification, just nothing special, just to having the knowledge of dimension of the range space and dimension of the null space. This is just easy verification. So now, is there any problem? Anything you want to ask regarding the um, this course content till now? Whatever I mean, I think up to week 4 content is uploaded. So if there is any doubt up to week 4 content, you can ask. And of this tutorial session, if is there anything we have not understood, any questions you want to ask, you can ask. Otherwise, I'll stop in 1 minute. If you have not asked anything.
Sir, clear.
Huh?
Sir, everything is clear, sir.
Okay, okay. So if there is not anything, so I'll stop in next few seconds. You can leave
Okay, sir.
if you
Thank
want.
you, sir.
Thank you.
Hello.
Huh.
Hello.
Yes.
Sir, actually, I enrolled for this course late, that is by the end of January. It was 29 Jan. So I was not able to attend actually the video, these problem solving sessions. So, is there any provision that these problem solving sessions are recorded so
Yes.
that we can, go through these problem solving sessions if we have missed them before we appear for these NPTEL exams?
Yes, there is recorded. There is YouTube video. Actually, after this class, I'll upload the video and link. I'll upload the video in YouTube recording. I'm just recording this full video. I'll upload this video and YouTube, and I'll give the link in some. There is a Google Sheet I think given. Uh, so we have record. I mean, you have not registered, right?
No, no, sir, I have registered,
Hmm.
but I
Late
missed
register.
out two problem solving sessions of assignment
Okay,
1
okay,
and 2, and I am
okay,
not
okay.
able to get the recordings also. So,
Okay, so if you have not even get a recording, I will try to find. I will submit. Otherwise, you can mail me. I will just give you the. I mean, there is an there is a link of the drive where.
Sir,
Uh,
there is a section, sir.
yes,
Sir, there is section for sir these videos, sir.
I think yeah.
Problems
That's yeah.
solving session, sir.
Right,
Week
right. In
one, week
problem.
two, week three,
Right, right,
and
right,
last one problem solving session. Then there
right,
you
right,
can
right.
get
That's true.
these
That's true.
videos.
In the
there is
portal,
a
I mean,
section where these videos are uploaded.
Yes, yes.
not section. There is
Like
a
week
link of
zero,
that.
week one, week two, week three. Like
Ah,
you go there and
right, right,
find
right.
the
बट सर उसमें मैंने जाके देखा, उसमें वो ये प्रॉब्लम सॉल्विंग वाली वीडियोस नहीं है।
नहीं
I
प्रॉब्लम
think
सॉल्विंग में जाओगे आप तो वहां पर अंदर जाओगे तो वो फिर उनका बिट्टू सी
link.
लाइक
You will
मिलन
get a
कुमार
link
मतलब ऐसे
actually.
नाम दिया होगा फिर वहां